problem where a bullet hits a block of wood and then slides together off the table. Now, you had this problem as a free response question for practice the other day, but we're going to change it just a little bit. And I believe the change we're going to make is we're going to have actual masses of the bullet and the wood and an actual velocity here and an actual height. Excuse me. We're going to go through and solve this numerically, and then we're going to go back and solve all these parts algebraically, so we can compare how we have these two different methods. Okay, so let's go ahead and read the problem. So, a .22 caliber bullet has a mass of 3 grams and it's fired into a block of wood. The velocity is 850 meters per second. The block of wood is initially at rest, and it's on a frictionless table. Okay? The bullet's going to embed into the 5 kilogram block of wood, and they're both going to slide to the end of the table before falling off onto the floor. The table is 1 meter high and has a width of 5 meters. Okay? So part A says, find the velocity of the bullet wood after the collision. So the bullet and the wood have combined together after the collision. They're both going to be sliding off to the right with a certain velocity. We're going to call this V after. All right? So we're just going to jump right in. This is a typical collision problem, so we know momentum is conserved. So to solve part A, all we have to do is set up and say that momentum before the collision is equal to the momentum after the collision. All right? So, what are all the things in our system that are contributing to the momentum before the collision? Well, our system is going to be this. I'll draw this carefully. It's going to be the bullet and the block. All right? So the bullet and the block are our system. The bullet's moving, the block is not. So all the momentum is going to be coming from that moving bullet. All right, so all we have to do is find the sum of mass times velocity before and after. So let's see, for the bullet, the mass is 3 grams, it's going to be 0.003 kilograms times a velocity of positive 850 meters per second, plus the mass of the block, which is 5 kilograms, times the block's velocity, which is 0 meters per second, is equal to the mass of the bullet-wood combination, and I think that's going to be 5 plus 0.003 times V after. V afters are unknown in part A, so we're done with the physics. This is just algebra. Now 5 times 0, the momentum of the block initially is, of course, 0. So all we have here is 0.003 times 850. This is going to be 2.55, that's positive, is equal to 5.003 times V after. All right, we divide both sides by 5.003, the mass, and we get 0.5097 meters per second is equal to V after. And you know what? This is a positive value. It came out to be a positive number, so we know it's going to be to the right. And that's all you have to do for part A. Okay, so what about part B? It's asking you to find the change of kinetic energy of the system during the collision. Well, I already know this is not going to be an elastic collision. It's going to be inelastic because the bullet is going to embed into the wood. Whenever the two or more objects of a collision stick together after the collision, if it's a car crash or something like this, we know it's going to be perfectly inelastic. So we already know the answer to that, but let's go ahead and find the change of kinetic energy. So the change of any variable is just the final minus the initial. So here we have the kinetic energy after the collision minus the kinetic energy before the collision. All right? And so we know what we're trying to find is actually the sum of all the 1/2 mv squares for all the object after the collision minus the sum of 1/2 mv squared, I can't write, before the collision. Excuse me, this is how you spell before. And after doesn't have an S on it. I don't know what's going on here. Okay, so you got to get this order correct, and you got to remember the minus sign. Otherwise, it's going to be totally wrong. Now, what's the difference here between kinetic energy and momentum? What's the big difference? Kinetic energy is a scalar, and momentum is a vector. So for momentum, we always have to be thinking about at least plus or minus. And at worst, we have to be thinking about x components and y components as well. Kinetic energy is just always going to be a positive number. But the change of kinetic energy can definitely be negative. Okay, so after the collision, we have 1/2 the mass, and this is going to be the combined bullet and wood together, is that. The velocity is 0.5097 meters per second. You got to square this. Okay, that's the only object after the collision. And we're going to subtract, put a big parentheses here. 1/2 times 0.003. That's the mass of the bullet. The velocity of the bullet is very high, 850 meters per second. Don't forget to square that. Plus the kinetic energy of the block. And I'm just going through the motions here. We know the kinetic energy of the block is going to be 0 joules. Okay, before the collision, it's going to be 0 joules. So all we have to do is subtract these. Again, we're done with the physics. This is just algebra. Okay, so after the collision, we get 0.65 joules. And before the collision, it's actually going to be a really big number. It's going to be 1,083.75 joules. That's the kinetic energy of the bullet. Guys, this is the whole point of having bullets go fast. You want them to have a lot of kinetic energy so they can do a lot of damage when they hit a target. Okay, and subtracting, we find something very interesting. Look at this. The kinetic energy lost, almost all the kinetic energy has been lost. We have lost 99.94% of the kinetic energy of the original bullet system. Okay? So we've lost almost all the energy of the bullet, but not all of it. Okay? That 0.06% is going to be responsible for moving the bullet and the block together. And it is so inelastic. Not even close to being elastic. So inelastic. Okay, so that's part B. Now, part C, so we got A done, we got B done. Part C is asking, how far horizontally from the edge of the table does a bullet land? Or does a bullet wood land? Well, let's think about what's actually going to happen here. This is what I like to call a frictionless table problem. You know, it actually comes up surprisingly often, and you probably have about a 50% chance of seeing it on the actual AP test when you take that test. Something like this. Okay, something happens to set an object in motion. It's sliding along a frictionless table, okay, and then it gets to the end, and then it lands. And you got to figure out how far away it landed. Well, how do you do this? It's projectile motion, guys. It's projectile motion. It's basic two-dimensional kinematics. So when this block gets here, 5 kilograms and change, it's moving horizontally with a velocity of v after, right? as it's moving horizontally, that horizontal component of motion is not going to change. Okay? But the vertical component of motion is going to change. This is the whole idea of two-dimensional kinematics. Your horizontal, your Vx does not change, but your Vy will change. So all we have to do here is treat this as a horizontal launch problem where the trajectory is going to make half a parabola. And you know what? We don't even need to know what the trajectory actually does. All we need to do is find one thing: the time. How much time is it in the air? We know, since the Vx is going to be constant, we know that the change of x is equal to Vx times the amount of time it's in the air, right? So how far it goes horizontally during that flight, quote unquote flight, is going to be this. It's the velocity in the x component times the time. And guess what? We just found in part A, we just found the velocity in the x component. So it's going to have 0.5097 meters per second horizontally here. It's going to keep going at 0.5097 because it's a frictionless table, okay? And then it's going to scoot right at the end, and the horizontal component is going to be 0.5097 until it hits the floor, and we don't know if the floor is frictionless or not. If it was, it'd keep going at 0.509 meters per second horizontally. Okay, how do we actually find the time? Well, there's a relation that we need, all right? So if we have a horizontal launch problem, we know that your change of y is equal to 1/2 gt squared, okay? So in other words, the height that we drop is going to be equal to 1/2 gt squared. Now, in this case, our height is a known, g is a known, we're trying to find t. So all we have to do is rewrite this equation to solve for t. And if you do that, you find the time is the square root of 2 delta y over g, okay? Where g is a positive 9.81. But we're not really going to call this delta y. Why don't we just go ahead and call this the height of the table? Oops. All right, we'll just do it this way. And that gives us an equation for time. All right, we're given the height of the table is 1 meter. So let's go down and go ahead and do part C. So part C, all right, we know that this is true because Vx does not change. We don't have an acceleration in the x direction when we're falling straight down, or when the gravity is pointing down. So that's going to be equal to 0.5097 times the time, okay? And the time is going to be equal to the square root of 2 times the height, which is 1 meter, divided by 9.81. So the time is equal to, well, here. I'll skip the algebra at this point. The time is just equal to 0.4515 seconds. Okay? So we plug this into our equation here, and we get delta x is equal to 0.23 meters. And that's all we need. So that's how far away it lands. And again, this is a super common type of problem. We have something sliding on a frictionless table, and they're really just testing you on whether or not you can recognize this as a projectile motion problem, a horizontal launch problem. All right, and part D, it's going to say qualitatively. That means no numbers, no specific numbers. Qualitatively speaking, how are these answers going to change if the bullet passes through the wood instead? Okay, so we're just going to do this right here. If the bullet passes through the wood, okay, what's the velocity of the bullet would after the collision? So how fast will the wood itself be going if the bullet passed through the wood? Well, momentum before is still going to be equal to momentum after, but now this right-hand side would change. We'd have to say plus the momentum of the bullet after it's passed through the wood. And since the bullet still has some momentum, that means the momentum given to the block is going to be less. So the block would basically be going slower. So the velocity is going to be slower. Okay, the change of kinetic energy, it's going to decrease less. And the reason for this is because the bullet is still going to be moving after the collision. By definition, if it's passed through the wood, it's moving faster than the wood. So it makes sense that it's going to decrease less. And how far horizontally from the edge of the table, in this case, would the wood itself land? Well, it's going to land closer to the edge. Vx for the wood is going to be less, so it's going to land closer to the edge. All right? Now, that's just conceptually, it's just qualitatively, with no numbers. That's how it would work. Okay, so now what I'm going to do is this. I'm actually going to go through this again, and we're going to answer all these questions algebraically. We're going to answer all these questions algebraically, and let's see if I can make some more space here. All right. Excuse my housekeeping here. Okay, that should do it. So, part A, we're going to solve it algebraically. Now, when we're solving something algebraically, I want you guys to think about it like this. Okay? I want you guys to think about it like we have some sort of computer program, right? And the computer is going to take as inputs, it's going to take everything we had a number for before. So it's going to take the height as a variable. That's going to be an input. It's going to take the velocity of the bullet as a variable. That's an input. Let's use little m for the mass of the bullet. Okay, that's going to be an input. Let's use big M for the mass of the block. You know, that's an input. And you know what else? G. We're going to leave G as a variable. So that's an input. What's going to happen is we're going to get some equations that only have these variables in it. So these equations are going to be like a little computer program, right? And we're going to get 3 outputs for the numerical answers. So if it took in these variables, our equations would give us V after for part A. It would give us the change of kinetic energy for part B, and it would give us delta X for part C. Okay? So we have the inputs and the outputs, and what we're writing is actually what goes in here. So we're writing the mathematical instructions, okay, that are going to give us these outputs. Okay, so let's go ahead and get started. Need a big eraser. All right, we're going to go ahead and get started with part A. So, again, we know momentum before is momentum after. Well, this is going to be the mass of the bullet. This is going to be the velocity of the bullet. And this is going to be the mass of the block plus the mass of the bullet. And this is going to be V after. We'll just leave it in the form V after, right? So we would have algebraically mv plus 0, right, is going to be equal to m plus m. That's the mass of the bullet block together times V after. And so we divide both sides by m plus m. Okay, we know it's going to be a number, m plus m, and we get V after is equal to little m, mass of the bullet, V, divided by m plus m. And that's our algebraic answer. You know what this is? This is it's like a general solution to this exact problem. So if I gave you any numbers for the mass of the bullet, the velocity, the mass of the wood, and so forth, and the height of the table, you could then find, well, how fast is a bullet going to be going after that collision? And that's the power of the algebraic solution, all right? In fact, I really did this. I really plugged in the numbers for M, V, capital M, and M, and I actually plugged it in, the ones we use, and I got V after is equal to 0.509 meters per second. So it works. Did that just for you guys. Okay, we're going to scooch down, and we're going to use this again later in the other parts, in part B and C. So let's remember this. We're going to go down to part B. Now it's saying, what's the change of kinetic energy before and after? Okay? So we've done all this. Now let's get to this part right here. Okay, so remember, this is the kinetic energy after, and this is the kinetic energy before the collision. So what is that, 5.003? Well, that's the mass of the block plus the mass of the bullet. This is going to be V after squared. Okay, and over here, well, that's just the mass of the bullet. Oops. And this is the mass of the this is the velocity, excuse me, of the bullet before the collision squared, and then this is still just 0. So our algebraic solution looks like this. Delta K is equal to 1/2 m plus little m V after squared minus mv squared. Oops, almost forgot the 1/2. Minus 1/2 mv squared, okay? And then, of course, this is still just 0 right here. But we're not really done yet, right? Because remember, V after is not going to be, it's not going to be one of those inputs for our little computer program. So we don't know V after, so this is not going to be useful if someone's inputting what was known in the original problem, right? So we have to actually substitute, we have to make the substitution for V after. So watch this. Delta K is 1/2 m plus little m, and this is going to be, all of this is going to be squared. It's going to be mv over m plus little m squared, and then minus 1/2 mv squared. Okay, so technically now we're done. I like to simplify this. I simplify it to the point where it's just too hard to make the next step, okay? So whenever you square a fraction, the top and bottom are both squared. So we have mv squared on the top, and we have m plus m squared on the bottom. Okay. And I'm going to actually simplify this by canceling out. I'm going to treat m plus m just as a single variable. And look, we have m plus m squared on the bottom. We have m plus m over here on the side. So this is going to cancel out with the 1 of the m plus little m's down here. And so what we're going to get is, and I'm going to just call this our final answer, it's going to be 1/2 mv squared divided by m plus m. minus 1/2 little mv squared. Okay? And now we have something that's very useful. In fact, again, I really did this. I plugged in the numbers for the mass of the bullet, the velocity we used, all this good stuff, and I got the change of kinetic energy is negative 1083.1 joules. So I got the answer we got. And this, again, is the algebraic form of the solution to part B. Hopefully these steps make sense. Hopefully these steps make sense. Okay. And then the last part down here, part C. Now, we already know that time is going to be the square root of 2h over g. We're even leaving g as a variable, right? So it's known, but it can be any number. We can plug in a value for the surface gravity of Mars if we wanted to. Height is height of the table. We can make that table 500 feet or 500 meters tall if we wanted to and see what would happen. Okay, so we've solved for Vx, so that's just going to be V after. And again, we're going to have to use the substitution. And then this is going to be the square root of 2h over g. So our algebraic form of the solution is going to be V after times the square root of 2h over g. But again, we don't know V after. We're not given V after in the original problem, right? All we're given is the velocity of the bullet before, the mass of the bullet, and so on. So we're going to use this substitution here again. So our final equation will look like this. It's going to be m little mv, big M plus little m, and I'll put this in parentheses, times the square root of 2h over g. And that's the algebraic solution for part C. And yes, I really did go in and plug in all these numbers, okay? And I got delta x is equal to 0.23 meters. So now we see there's two ways to do this problem, right? There's the direct, you just plug in the numbers immediately kind of way, and there's also the algebraic kind of way, where you solve everything in terms of the variables and then you plug it in. The algebraic way, it can be more abstract, right? So it's more abstract while you're working through it, but in the end, you can see cool things. Like, for example, mv is the momentum of the bullet. And we can see that delta x is proportional to mv, right? So if everything else is kept the same, if we tweak the momentum of the bullet, delta x is going to increase. If we double it, delta x will be twice as much. So we can see neat things like this. Okay, one last point. I want you guys to think about the quadratic formula, right? So the quadratic formula is going to solve an equation, a general equation, in the form of this. Now, if I were to give you, just like 2x squared minus 3x, plus 1 is equal to 0, you could go out and solve this, completing the square every time, but having a formula to solve out for x directly using a, b, and c is going to be faster in a lot of ways, and it's going to be less prone to making mistakes. Okay? So that's all I want to say about that. All right. Thanks for watching. Have a good night.